Good morning. So, we will continue with this topic, third topic, that is on dye-sensitized solar cell, quantum dot sensitized solar cell, perovskite solar cell and tandem solar cell. So, regarding dye-sensitized solar cell, what we had discussed in the previous lecture is that it is actually a kind of solar cell which came after p-n junction solar cell with a modification with respect to p-n junction solar cell, that the charge carriers here are generated in one particular object or one particular material, which is a dye or photosensitizer, and then it is transported to another material which is in wide band gap semiconductor, that is TiO2, and then it follows the circuit and reach to the counter electrode. In case of p-n junction solar cell, what we have seen is that the charge carrier generation and transport both take place in one particular medium. Here the charge carrier generation takes place in dye and the transport takes place in a wide band gap semiconductor, where the dye molecules are anchored. And then of course, there is an electrolyte in between two electrodes, which actually works as a medium for charge carrier transport, and it gives us energy or power when the electron moves in the outer circuit through outer circuit to a load. Okay, so, this is the basic principle of a dye sensitized solar cell, and when we talk about quantum dot sensitized solar cell, it is almost same as dye sensitized solar cell, where dye, which is generally an organic material, is replaced by quantum dot, which are inorganic semiconductors, and therefore, some variation which we get in quantum dot sensitized solar cell in terms of band gap tunability and multiple exciton generation, which we have discussed in the in our previous lecture. Now, what we will see in this lecture, we will again look at the dye sensitized solar cell and quantum dot sensitized solar cell, and with some question answer, so that some of the issues which we have discussed, we will make a detailed elaboration on this topic. So, let us see that what are the things which we have discussed. Some questions let us ask. What is HOMO and LUMO? So, we discussed about HOMO and LUMO, and what HOMO stands for highest occupied molecular orbital and LUMO stands for lowest unoccupied molecular orbital. And when we consider these two, HOMO and LUMO, we actually consider what is known as molecular orbital, and for the organic material the molecular orbital are important. Okay. So, suppose when we arrange an electron in an orbital and then we bring this electron very close, then orbital actually overlaps, and when we make a molecule, it forms a molecular orbital in a very simple manner, that if I have an atom X here with a spin up, two atoms X spin up and they come closer together and form a molecule. And what will happen when they form a molecular orbital? It actually form a level which is highest occupied molecular orbital and another level which is lowest unoccupied molecular orbital. And then there is a gap which is known as HOMO-LUMO gap. Okay. So, it is similar to what we know about valence band and conduction band of a semiconductor, which we discussed in topic 1, and then the band gap, which is the the difference of energy between conduction band minima and valence band maxima. So, here also we have a gap. So, this is a typical the configuration of HOMO and LUMO in ground state. So, you can see HOMO, all the states are filled up with electron, okay, and the LUMO, all these states are unfilled. Okay. And then when we excite this particular molecule or the organic material which is used or a dye which is used in a dye sensitized solar cell, the electron from here gets excited and it goes to from HOMO to LUMO, crossing the gap if the energy of the incident photon is sufficient to excite it from HOMO to LUMO. Okay. So, now the question is how this conduction band is populated in dye sensitized solar cell. Okay. So, we know that conduction, in order to populate the conduction band of TiO2 which is connected with this dye, so this is a typical say position of LUMO and this is HOMO, and then TiO2 is connected with TiO2 or the wide band gap semiconductor which is used, where actually the dyes are anchored on it. Okay. So, this is the energy level of conduction band say edge or conduction band minima. So, how it is populated? So, when electron goes from HOMO to LUMO, it actually comes to the conduction band of TiO2. Okay. So, there are two stages where this conduction band of TiO2 or the wide band gap semiconductor which is used in dye sensitized solar cell are populated. The first step is the photo excitation of electron from HOMO to LUMO in the dye, and then transfer of this electron from LUMO to the conduction band of the TiO2 or wide band gap semiconductor. Okay. So, let us look at the next question. Identify the reactions in DSSC for oxidation of photogenerator and dye regeneration. So, we have discussed that there are various reactions which takes place in a dye sensitized solar cell after the light interacts with the dye, and just now we have seen that after the electron goes to the HOMO state of the dye, it actually transferred the electron to the conduction band of TiO2. Okay. So, let us look at again what are the reactions actually we discuss when we discuss the operation of a dye sensitized solar cell. So, S is a state which is actually the state of a dye which is absorbed in TiO2, and then it interacts with the photon which is falling on the dye, okay, and it goes to excited state S star, that is also absorbed in TiO2. Okay. So, this is the first reaction. So, this is the photo excitation reaction, okay, or photo generation reaction, where dye goes to excited state. Now, this dye which is absorbed on TiO2, it becomes S plus by injection of an electron to the conduction band of TiO2. Okay. It is an injection process of electron in the conduction band of TiO2. all right. So, now it gives an electron to TiO2 and the third reaction starts when S plus, which is absorbed in TiO2, it interacts with I minus of the redox couple, which we have discussed in dye sensitized solar cell. You have I minus and I 3 minus redox couple in the electrolyte, and then it comes back after getting this electron, that is the HOMO level of the dye, it gets the electron and it is regenerated, okay, and gives rise to I 3 minus. So, these are the two important reaction. This is one reaction, this is another reaction. Which we consider as the first one as either the injection of electron in TiO2 or the same way that as S star gives an electron to the TiO2, it gets oxidized. So, these are the two steps which are asked in the question, but of course, we should look at all other steps also. So, once we have this I 3 minus, it gets an electron from the cathode or the counter electrode, and then it becomes 3 I minus. Okay. So, these are the major equations which work. Apart from that, there are some recombination equations which we will see in the later discussion. Okay. Now, in energy level diagram show electron relaxation path. So, this is what I was discussing, that what are the relaxation process, because when we see that this is LUMO, this is HOMO state, and this is a conduction band of TiO2, all right. And then LUMO is, of course, there are different electrons in the state, there is valence band of TiO2. Okay. So, we have seen the generation process, there are different electrons in HOMO. After photo excitation, electron goes here, okay, electron goes here in LUMO, and then they are transferred here. So, this is a generation process, this is also a generation process, but the electron can come back from here, from LUMO to HOMO. So, this is one path of relaxation or recombination. In other way, this electron can directly from the conduction band can come to the HOMO state. So, this is another relaxation path. Okay. Or this electron which is there in the conduction band, instead of transporting to the TCO which is connected with the TiO2, can jump to the redox potential level of electrolyte and can make another relaxation or recombination path. Okay. So, these three are the recombination or relaxation process which are continuously acting, we can say, the against the photogeneration process. So, photogeneration process are identified, the one the one which is the red line, where this one is a photogeneration process, this is also a photogeneration process because it populate the conduction band, and then this electron in principle flows in this direction and goes to the counter electrode in order to make the circuit complete through a load. Okay. So, recombination process, as we know in solar cell discussion, in our previous discussion also, it is always something which reduces the current density and overall reduces the fill factor and efficiency of a solar cell. So, therefore, one is to be very careful with this recombination path or relaxation path of electron in case of dye sensitized solar cell also, and design the material in such a way that this recombination or relaxation of electron, which is against the photogeneration process, are suppressed. So, now let us ask another question: what is the role of electrolyte in DSSC? What are its essential properties? So, we have seen what are the major components of a DSSC. Okay. So, one component is dye, another is the wide band gap semiconductor, say TiO2, and then of course, this photoanode, and then the counter electrode, and one important component is electrolyte, which we discussed in detail during our lecture. So, what are the essential properties of electrolyte? The first property of the electrolyte is, so what we see that in the previous question, that electrolyte should be involved efficiently in dye regeneration process. Okay. That means, it should populate the HOMO of the dye efficiently. So, that you have number of electrons again ready for photogeneration. So, it should efficiently do the dye regeneration. Okay. The second thing is that charge carriers actually gets transported through the electrolyte. Okay. So, the diffusion of charges through the electrolyte should be efficient. So, if the charges cannot flow properly through the electrolyte, it will be again get recombined, and then it will not come into any action of that solar cell. Okay. So, therefore, the efficient charge carrier diffusion. Third important property of an electrolyte is that the light comes and it not only shines the dye, the electrolyte is also facing the light. Okay. So, it has also some kind of absorption band, light absorption capability. So, that should be completely different from the absorption band of dye. Okay. So, the absorption edge of electrolyte should be different from that of dye. So, there are three major important properties of an electrolyte which is used in dye sensitized solar cell or in quantum dot sensitized solar cell. All right. Of course, one is to be careful. Another very important property of the electrolyte should be, it should not corrode the system. Okay. It should not disturb the system by any process of corrosion. Okay. So, it should not corrode the okay, because entire system is inside the electrolyte and it is a chemical and it should not actually corrode that system. If it starts disturbing the system, then the efficiency of the cell will go down. So, these are the important properties of the electrolyte which one is to consider before one selects an electrolyte. So, let us look at few typical case studies where people have demonstrated how the IV characteristic of DSSC varies with different the physical quantities. Okay. So, what we have seen in case of dye sensitized solar cell, of course, there should be very efficient photogeneration process, efficient electron injection process, and then efficient flow of electron from the photoanode to the counter electrode through the outer circuit. Okay. So, anything which is against that, suppose the recombination process, it always disturbs the solar cell, or it reduces the efficiency, it reduces the current density. So, we have to see that what are the quantities that one should know, that what is the controlling parameters. So, one important controlling parameter is the mobility of the charge carrier. So, the question is the IV characteristic of different solar DSSC of different mobilities are shown here, and we have to explain that graph. So, you can see that there are 4 IV characteristics are shown. Okay. So, this one corresponds to maximum electron mobility, which is 3 centimeter square per volt second, and this is 10 times less than that, 0.33, and this is again 10 times less, and this is the lowest. So, one is 0.03, another is 0.003. So, you keep on reducing the mobility. Okay, this is very typically, it can be done in theoretical calculation, and this is shown in a theoretical work only, that if you systematically reduce the mobility of electron by 10 times, then how this IV characteristics varies. So, if you look at y axis, you see that the current density or short circuit current density, which is very high here, almost 100 ampere per centimeter square, eventually reduces and becomes almost 20 ampere per meter square. This is a really significant reduction in the current density, and why it is happening if you change the mobility of electron. So, again you think about the situation where this conduction band of TiO2 is populated, and then electron moves very fast when it is mobility is high. So, this is the TiO2 conduction band, and this is valence band, and electron is here, and it is moving fast in the circuit. Okay. Then what will happen? The recombination probability will be less. In other words, what it means that if we reduce the mobility of the electron, electron will have a chance to recombine. So, I have already shown you the relaxation path or recombination path. So, electron may not take this path. Okay. Instead of that, it may relax back to either to the HOMO level or to the redox level. Okay. So, this is a typical situation which happens in a dye sensitized solar cell. So, we have to look at, in order to make the current density higher, we have to really check that the electron flows in this path efficiently, and therefore, its mobility should be high. So, therefore, we get a higher current density, and you can see that it is significantly higher, and it reduces drastically when the mobility increases. Okay. But now, we come to the another side of the axis. You can see there is a little variation in the open circuit voltage also. In fact, the case where the electron mobility was maximum is having little less open circuit voltage, very insignificant, but little less open circuit voltage as compared to the one which is having lower electron mobility. So, what is the reason for that? So, if you just recollect that when we talk about open circuit voltage of a DSSC, what essentially we mean is that this is a conduction band minima of TiO2, and suppose this is the Fermi level of TiO2 and this is the redox level of electrolyzer or electrolyte, then this particular difference, that is EF, is actually what is known as open circuit voltage. So, now what happens if electron moves very fast in the conduction band? It is moving very fast when the mobility is higher. Okay. So, that means the conduction band is getting depleted of electron. In other words, when electron stays there because of lower mobility, suppose the last case this one, if electron stays there, Fermi level goes little higher, little up, because the conduction band is populated. Okay. If Fermi level goes little higher, then this VOC goes little high, okay, because the difference increases, and therefore, there is a little enhancement in the Fermi level. You can see a little enhancement in the VOC, open circuit voltage, when the mobility is less, but it is insignificant. The significant thing is that there is a huge enhancement in the short circuit current density, and which actually gives a very good IV characteristic with high fill factor and higher efficiency. Let us look at another important physical parameter, that is dye uptake. Okay. So, what is the meaning of dye uptake? Meaning of dye uptake is that we know that the TiO2 or the wide band gap semiconductor, this is mesoporous. Okay. So, you can put lot of dye in that in TiO2, and you can interest depending upon how much dye this one particular wide band gap semiconductor or one TiO2 which is having better structure, mesoporous structure as compared to another TiO2, how much it can take up dye. Okay. So, one particular estimation is that this is a, we can say 1 into some concentration C dye, and this is 1.5 times of that, this is 2 times of that, and this is 2.5 times of that. So, you can see when the dye intake is increasing, this is the way it is increasing. So, this is a maximum where dye uptake is maximum, and again you see that short circuit current density is very high. Here it is almost 130 ampere per meter square. Okay. And then when we come to here, that is 1 into C dye, it is approximately you can say 82 to 83 ampere per meter square. So, this is a significant reduction in current density when the dye uptake in the DSCC is reduced. Okay. So, what is the reason? It is very simple to understand, because if we have more dye uptake, we have more electrons which can go from HOMO to LUMO and populating the LUMO, and eventually the large number of electrons are injected to TiO2, which takes place in the transport process. Okay. So, it is very clear that if we have more dye attached to the semiconductor or TiO2 here, then definitely there will be more charge carriers which will come on the conduction band or injected to the conduction band of TiO2 and take part in the process. Okay. And therefore, eventually increasing the short circuit current density significantly higher. But if you look at these open circuit voltage, here also we can see the marginal change. Here the open circuit voltage also increases with dye uptake. Okay. Considering the mobility is same, in the last question we have seen the mobility is different. Now, but now it is a case where the mobility is same. It is only the number of electrons which are more. So, if the number of electron is more, again we come to same picture So, this is TiO2, this is conduction band, this is valence band, this is Fermi level. So, if I have more number of electrons here because of higher dye uptake, okay, then the Fermi level will go up, and this is a redox level. Okay. So, this is the difference, which is VOC. Is Fermi level goes up, then VOC, which is actually a difference of Fermi level to redox. Okay. So, this will also increase accordingly, Fermi level goes up. So, that means, if we populate more this conduction band of TiO2 or the semiconductor, the VOC will increase, but that enhancement is not that significant. The significant enhancement is seen in case of short circuit current, and therefore, eventually it improves the fill factor and the efficiency of the solar cell. Okay. So, now I come to a point where we have two different counter electrodes. So, the question is, the IV characteristic of a DSSC with carbon and platinum counter electron are shown below. So, it looks like this is for platinum and this is for carbon. So, visually it looks like that the platinum as a counter electrode gives a better performance as compared to carbon. Okay. So, what happens, you can see that first let us look at the short circuit current density. So, it seems that when we use platinum instead of carbon or any carbon compound as the electrode is higher short circuit current density, and it is also reported in this literature that it also has higher fill factor as well as higher efficiency as compared to when we use carbon as counter electrode. Of course, when you use carbon as counter electrode, there is a little enhancement in open circuit voltage, okay, but the overall performance with platinum is better. So, it seems that the reaction of carbon with electrolyte and the reaction of platinum with electrolyte are different. Okay. So, the kind of interaction which takes place with electrolyte and counter electrode, that will decide that what is the recombination and regeneration. All right. So, if we have platinum or if we have carbon, this interaction, if it leads to more recombination, okay, that will definitely reduce the current density which is happening in case of carbon. And then if it also has a better regeneration, this is also happening in case of carbon only, then because this is again populating the HOMO level of dye, and that is this electron is again going back to the LUMO of dye. So, therefore, these are all connected, and therefore, if the regeneration process is better in case of carbon, it will give a higher VOC, because again the Fermi level will go little up and therefore, VOC will increase. But anyway, overall the platinum is a better counter electrode as it is nicely demonstrated here. Now comes what are the important properties of dye. Okay. So, one property is definitely it should have a capability of absorbing light from a large spectrum of the solar cell, better absorption capability. Across the solar spectrum. Number 2, as I just now I mentioned that if you have more and more dye which are attached with the TiO2, you have better and better performance of the solar cell. Okay. So, therefore, the addition of dye should be higher with a particular wide bandgap semiconductor which is used for that particular DSCC. So, what we should mention that better adhesion to a particular semiconductor. And third is, of course, the important point is that it should be stable, because you see that the die in the entire system of DSCC, it is connected with a semiconductor, then it is also having in the electrolyte which is flow on this particular cell, and therefore, they are sort of placed on that electrolyte. So, therefore, its chemical and thermal stability should be high. Okay. So, these are the three most important properties of the die which is required for a design of a good DSCC. And of course, it should have the capability of accepting electron when the regeneration of dyes take place. Okay. So, now we come to few questions related to quantum dot sensitized solar cell. So, what are the problems with dye sensitized solar cell which can be overcome by the quantum dot sensitized solar cell? So, just now we mentioned that in dye sensitized solar cell we have organic dye or natural dye, okay, whatever we are using, but you remember that they are generally soft material, organic material. Okay. So, in case if we require an electrolyte or a a dye sensitized solar cell which works in an environment which is relatively harsh, then the stability of the dye becomes a major concern. Okay. So, therefore, we need a sensitizer which is not organic in nature, and that was actually done in case of quantum dot sensitized solar cell. So, the dye which is organic material were replaced by inorganic semiconductor like cadmium sulphide, cadmium selenide, lead sulphide, okay. Because they are inorganic. So, they are more stable. So, this is one important, or you can say a major problem which is there with dye sensitized solar cell can be overcome in case of quantum dot sensitized solar cell. Additionally, when we use a dye sensitized solar cell, its HOMO-LUMO gap is fixed, that is what we discussed previously. But if we take a quantum dot sensitized solar cell, we will see again, we discussed also in our previous lectures, that one can tune the band gap and one can have combination of quantum dots, so that there is a band gap tunability. If the band gap is tuned, then the absorption edges are tuned. All right. So, this is an extra capability of quantum dot sensitized solar cell. And another important point which we discussed in our lecture, that it is also having multiple exciton generation capability. That means, for a single photon it can generate more than one charge carriers which can be used in the transport and the action of the solar cell. So, these are the major advantages of the quantum dot sensitized solar cell and using quantum dots to replace the dye. Now, we come to again this point which I discussed just now, the tunability of band gap and where it is essential. So, you look at this when we consider a bulk material, what happens in case of a bulk material, we have a fixed say conduction band and valence band, and there is an energy. Now, we know that if I just consider the electrons are in a potential well, okay. So, we mentioned that in the potential well its energy eigenvalue depends inversely to the length. So, there is a spread in the energy level when you consider a quantum dot. So, what you see is that now in case of quantum dot, this is a valence band and this is a conduction band, and there is a discretization of energy level because of the quantum confinement of electron in the quantum dot. Okay. And that actually enhances the band gap or the energy, and this actually eventually gives a very good property related to absorption. So, let us look at this. When we change these CDSC quantum dot sizes, say from 2.2 nanometer to 5.5 nanometer, you can see the absorption edge continuously changes. It goes to lower wavelength side or higher frequency side or higher energy side. So, that means it is having a capability of tuning the band gap, and if we look at the luminescence also, it goes from higher wavelength to lower wavelength, that is lower energy to higher energy. And if we really look at it, what is the color we observe? So, you can see which is very nicely demonstrated. So, this is a 3 nanometer quantum dot, this is a 5.5 nanometer quantum dot, this is 7.5 nanometer quantum dot, and this is 8.3 nanometer quantum dot. And how color changes beautifully. So, it starts with a green color, becomes yellow color, and then eventually it becomes close to red color. Okay. So, that means if we change the quantum dot size, okay, we actually change the band gap, discretize the energy level, and also control the absorption of light and also the emission of light. So, there is a beautiful demonstration of the property of a quantum dot and the quantum confinement. Okay, so, the last question is related to the semiconductor, where these dye sensitive dyes or the quantum dots are connected or attached. So, what we mentioned that there should be a mesoporous semiconductor which should take up these quantum dots and dyes, and what are its essential property, because if we have a better mesoporous structure, then the first thing which we can have the higher surface area. So, if we have a higher surface area of the TiO2 or the wide band gap semiconductor, then definitely we can have more dyes or quantum dots uptake. Okay. The second is better transport of electron. Okay. So, we have to have a medium, because once electron is produced in or goes from HOMO to LUMO and it is injected to the conduction band of TiO2, it actually has to go through this entire it has to cross through the entire TiO2 before it comes to the TCO which is attached to that. Therefore, the transport should be very good when we consider a particular design of TiO2 or the porosity or the mesoporous TiO2. Okay. The third thing which is important, because TiO2 is a wide band gap semiconductor. Okay. Being a wide band gap semiconductor, it is actually the transmission of light through TiO2 is quite high. Okay. So, therefore, when we make a mesoporous structure, it is also sometimes it hinders the electron path. Okay. And in some cases people have seen that one can change the absorption edge of TiO2, control the absorption edge of TiO2, so that the electrons can be efficiently injected to the TiO2 by some doping process, which is an extra the properties which one can add to the mesoporous TiO2. Okay. Okay, so today we stop here, and in the next class we will continue with this question answer session of this third topic. Thank you.